In this video, I want to talk about fluid force. Essentially, we're looking at something like, let's just say we got a dam holding back some water. So I'm looking endo on the dam here. And I want to know that water is pushing against this dam. And I want to know how much force is there so that I can figure out whether my dam is going to be strong enough to hold that much. Or maybe to think of it more in terms of how strong do I need to make my dam to hold back that much force. So to do this, I'm really bad at remembering formulas, so I need to be able to figure them out. And here's the way I think about how to solve this. Fluid force is about weight pushing against some little bit of area. And so what I'm going to do is I'm going to start with a little bit of area. I'm trying to draw this in 3D. So I got this little bit of area down on the bottom, which I'm just going to call dA, so a small amount of area. And on top of that area, there's a column of water. Right? I'm just trying to figure out how much weight is pushing down on this bottom edge, this bottom surface there. So if this is the depth of the water here, then the volume of that water, volume, not volume, how about volume, is going to be the depth times this small amount of area, dA. Okay. If I then multiply that volume times the density, so we have that would be, that's the weight density as opposed to mass density. So the weight density of water would be 62.5 pounds per cubic foot, or in metric you might say 9,800 newtons. That's supposed to be an NT, newtons per cubic meter. Okay. You got to be careful because sometimes in metric they'll give you the mass density. They'll say kilograms per cubic meter, in which case you then have to multiply that by the acceleration of gravity to get the force. Okay, so the force, the weight essentially that's sitting on this base down here is given this way. The force is the density times the depth times a little bit of area that's on the bottom. That's the force that's pushing downward, right? Pushing downward. But the crazy thing about fluid force is that it pushes in all directions at the same time. So the little fluid particles are all bouncing off each other, and they're pushing, but they push sideways as much as they push upwards or downwards, which you wouldn't have to worry about if this were solid. I mean, if you're talking about wintertime and all the water freezes, then gravity is pulling it downward and it just goes downward. There would be no force against the dam. In fact, if this were solid ice, then you could just erase your whole dam, get rid of it, and it would just all stay there. Right? Liquid doesn't work that way. Liquid forces in all directions the same as it's being pulled down by gravity. So notice here that there's density times depth times a little bit of area. So I think of this in terms of, well, being an American, I think in terms of pounds and feet. So this is like density would be pounds per cubic feet times depth, which is just feet, times area, which is square feet. And so you can see that the labels here, the cubic feet, feet, and square feet would all cancel out, leaving just pounds, which is force. Right? But there's some other things that I see. The density times the depth, if you just multiply those two together, that would be pounds per square feet. This is what we call pressure. Right? Pressure is like pounds per square inch, right? That's the way you think about, that's the way I usually think about pressure. So if you multiply pressure times area, then you just get pounds. So sometimes that's the way this is presented, in that you're saying, what's the pressure times the area? Well, how do you calculate the pressure? Well, it's density times depth, and that just doesn't make as much sense to me as just saying, figure out the total weight that's sitting on this thing. You know, how deep is it? What's the area times the density? That's the total force. It just so happens that these first two things multiplied together tell you what the pressure of the liquid is at that particular depth. Okay. So the way we think about this problem now is we say, well, different parts of the dam are at different depths. So if we chop that dam up into a bunch of horizontal pieces, where essentially each slice going across is all at the same depth, or at least almost all the same, because you're calling it just a very tiny little bit of thickness. You have that thickness times the distance across would be a bit of area. That's your dA. Rather than the area being down and all the water sitting on it, you're thinking of it on the side here. You've got some length times some tiny little bit of thickness. And all that weight that's pushing down this way is also pushing sideways that way. So this area going across here times that same amount of pressure would give you the force on that little bit. So if I know the force on that little bit, and I know the force on this little bit, and this little bit, and this little bit, and this little bit, and all the little bits all the way up and down the dam, then I would know the total force on the dam. I'd have to add them all up. This is Calc 2, right? We chop things up into little pieces, figure out each piece, and then add them back together again. So let's do an example of that. Let's do an example, yes. Actually, let's do the example in the next video. That's the basics of fluid force. Now we'll use this to, in the next video, to do an example.